Greetings, everyone. So it is 2:15 Mountain Time. And before we get started, I'd just like to mention a couple of logistics. Hopefully you're all noticing that as opposed to some of the other sessions, this is not a Zoom meeting, this is a Zoom webinar. And so what we would like you to do is throughout the talk, if you have comments that you would like to send to people, feel free to please put that in the chat. And if you have comments directly for the panelists, which means me as moderator or speaker or our tech support, feel free to put those in the chat. If you have questions for the speaker throughout, please put those in the Q&A, and I'll be moderating the Q&A, and we'll make sure that those questions get through to the speaker. So with that kind of out of the way, I'm very excited. Thank you again, all of you, for joining us. I'm Aaron Lutman. I'm a mathematician at Pacific Northwest National Laboratory here in the US. And I'm also an officer of the Mathematical Association of America's Special Interest Group on Mathematics for Business, Industry, and Government. We're very excited about today's JMM 2021 MAA Invited Address by Ms. Angela Sheffield, a senior program manager at the US Department of Energy's National Nuclear Security Administration. Ms. Sheffield received her BS in economics from the US Air Force Academy. This was followed by 7 years in the Air Force, during which time she served at the Air Force Research Laboratory, at the Naval Air and Space Intelligence Center, and was also deployed overseas. And in addition to her service during her time on duty, she also earned an MS in Operations Research at Kansas State University. After leaving the Air Force, Ms. Sheffield became a senior staff scientist at Pacific Northwest National Laboratory in Richland, Washington, where you'll notice is also where I'm from, but we didn't overlap here. And here she developed and led research and development projects supporting the Department of Defense, Department of Homeland Security, and the intelligence community. She also managed, as a line manager, a team of R&D scientists in computing and analytics. Now, Ms. Sheffield is currently a senior program manager at the National Nuclear Security Administration's Office of Defense, Nuclear Non-Proliferation Research and Development. And no, none of us tries to say that one 5 times fast. But she leads a program to fast track the maturation of AI, artificial intelligence systems, to detect and interdict illicit foreign activities to develop nuclear weapons. She oversees a very large portfolio of diverse projects, working with scientists, engineers, mathematicians, and statisticians at over 200 world-class research institutions. Today, Ms. Sheffield will be sharing with us her vision for national security applications of next-gen artificial intelligence, pushing beyond basic machine learning, and also talk about opportunities for our mathematical and statistical communities to get involved, really showing a lot of great opportunities for our students and for those of you who are faculty to help guide your students into the US Department of Energy enterprise. So, Ms. Sheffield, if you would please put on your camera and take it away.
Thank you, Aaron. Thank you to the Mathematics Association of America and to Joint Mathematics Meeting and to everyone online here today. I hope that you are all well and that 2021 is off to a smooth start for each of you. As Aaron said, I'm Angie Sheffield. I'm a senior program manager at the United States Department of Energy National Nuclear Security Administration, where I run a research and development program to develop technologies to detect activities by state and non-state actors around the globe to develop nuclear weapons. I'm not seeing my slides. Are you seeing my slides? Fabulous. Awesome. In particular, research in my portfolio and my program focuses on advancing the state of the art in applied mathematics, computing and computational science, statistics, and data analytics in order to develop the next generation of artificial intelligence technologies that will enhance the United States' capabilities in proliferation detection. Today, I'd like to present the 5 research focus areas that make up our next generation AI program at NNSA. As I go through these, I'll talk about the mission and the mathematics that define these focus areas and share our research gaps and focus and future work with you, with the hopes of getting you excited about what I consider to be the hardest, most interesting, and most impactful area of AI R&D. Next slide, please. The nuclear age began 75 years ago with the detonation of the world's first nuclear bomb. That device was built in the United States under the Manhattan Project, a race to advance and weaponize nuclear science during World War II. But the nuclear age brought more than nuclear weapons. It also brought civilian applications of nuclear science and technology that transformed medicine and the energy industry. International policies prohibit the spread of nuclear weapons and encourage the reduction of existing nuclear weapons stockpiles. And they also protect the pursuit and use of civilian applications of nuclear energy and nuclear science and technology, peaceful applications of nuclear science and technology. In order to accomplish these two goals, both to ensure peaceful use of nuclear science and technology while still preventing the spread of nuclear weapons, the United States works with global partners to employ a suite of technologies, policies, and international programs that we refer to as nuclear nonproliferation. In particular, one subset of nuclear nonproliferation, proliferation detection, focuses on the use of technologies to detect and characterize observable activities and resources related to nuclear weapons development. Nuclear proliferation detection is itself as old as the nuclear age or the nuclear bomb. Immediately following World War II, the United States recognized the need to detect foreign nuclear tests and called for the development of technologies to detect atomic explosions around the globe. To do so, the United States leveraged the same scientific and engineering expertise, the same researchers and engineers, laboratories, and facilities that had developed nuclear weapons to advance the science and build technologies to detect them. This network of laboratories and industrial sites around the United States became NNSA, the Department of Energy, and the Department of Energy National Laboratory Complex. Next slide, please. It takes a lot of science and engineering to build a nuclear weapon. And in terms of that whole process to build a nuclear weapon, nuclear testing is at the very end. Global events, such as nuclear testing in North Korea, highlight the need for technologies to detect activities to develop nuclear weapons far earlier than when a program begins nuclear testing. Certainly, earlier detection would afford the United States and the global community more options for intervention. Today, the United States again calls for the development of technologies to detect proliferation, this time to detect indicators that present far earlier than when a program begins nuclear testing. The development of technologies to detect early indicators of proliferation is super challenging. But for this subset of proliferation detection problems in particular, AI presents new opportunities. Next slide, please. So already Aaron and I have both said AI a ton. What is artificial intelligence? At Department of Energy, we define artificial intelligence as a broad suite of technologies capable of solving problems and performing tasks that mimic human intelligence. And that phrase, mimic human intelligence, brings to mind other definitions of artificial intelligence, which speaks of intelligent agents, systems that seem to behave rationally, behave humanly, systems that perceive the environment, reason with what they perceive, problem solve, and act. Across the US government, artificial intelligence is recognized for its immense potential to transform like everything. So what is AI? AI is science fiction. We see it in movies, and I see calls for it in policy, recognition that this is a powerful technology that is supposed to make everything better, to make the world safer. And as an expert in nuclear nonproliferation and computing and analytics technologies, I do see through that hype. I see the potential that artificial intelligence has to transform how we do proliferation detection in the US government. But how do we get from science fiction to these new technologies? How do we get from aspirational policy to delivering widgets or code to a national security decision maker or analyst who's charged with finding bad guys? To do this, I translate this aspirational policy and I draw inspiration from science fiction and the scientific literature to develop a research agenda, an actionable strategy to advance the state of the art and build new technologies that will enhance and even transform US proliferation detection and national security. Now, for the highly specialized and high consequence domain of proliferation detection, off-the-shelf and conventional approaches to artificial intelligence, particularly machine learning, are insufficient. And it's not just a mismatch between what is available in commercial applications. really not all of the science exists yet to fully leverage these capabilities for this domain. Next slide, please. AI research and development at NNSA seeks to develop the next generation of artificial intelligence, by which I mean new science, new mathematics, new methods and new technologies to advance the state of the art and build systems suitable for national security, build systems that are useful in the proliferation detection domain. Research in my program is focused on 5 R&D areas, and these areas each map to shortcomings that limit the usefulness of existing methods to addressing problems in our mission space. I'd like now to walk through these 5 areas, beginning with the next generation AI requirement for robust models, particularly in situations of data sparsity, and the proliferation detection domain is data sparse. As I walk through these examples or these research areas, I'd like to describe the problem, and by which problem I mean I'm referring to the challenge in the mission in the nuclear proliferation detection domain that we're trying to accomplish, trying to solve by developing a new AI capability. I'll also cover a few of the unique challenges and considerations for using AI-enabled technologies for this mission, and highlight approaches developed by projects in my program to address or to advance the science in these areas. Finally, we'll look towards the future at outstanding research gaps and future work to close each of these, to address each of these research areas. Also, on my slides as we walk through this, you'll see the names and faces of researchers on projects in my program, particularly researchers who have backgrounds in mathematics and statistics. You'll also see for many of these folks, while they might have an undergraduate or graduate degree in mathematics or statistics, they may also have a complementary degree, either an undergrad or a graduate degree in another domain science. And that's really typical for researchers in the National Laboratory Complex. The national labs are charged with tackling the most challenging, complex, and multidisciplinary problems that there are, and it makes sense that many of our researchers have multidisciplinary backgrounds well suited for those problems. Next slide, please. In proliferation detection, we use sensors, measurement technologies, and detection algorithms to find observable signals and signatures of activities that indicate that someone is developing nuclear weapons. These signals and signatures tip us off to illicit activities or provide decision makers with evidence or actionable information regarding a nation or group's nuclear weapons capability. Yet, in the proliferation detection domain, it is an absolute certainty that the data and information you have access to when you're developing a sensor or training an algorithm is going to be really different than the data that technology is going to see when it is deployed. We have to build sensors and train detection algorithms knowing that we don't know and we will never have enough data to fully represent what the technology is going to see in the wild. I'll remind you that in proliferation detection, we don't know where the bad guys are. If we knew enough about where the bad guys were, that I could give you enough data to fully represent the environment and what that looks like in the wild, we'd have the bad guys. In proliferation detection, we also don't necessarily know what we are looking for. There are very few past examples of a program that has successfully developed nuclear weapons. And really, we don't know if we don't see any other past examples because they haven't happened or if we've missed them. We can't make any inferences about the population or what we expect based on those past examples. We're in this domain, this regime that calls to mind a phrase that is familiar to many of us, whether we have a national security background or a background in applied mathematics and predictive modeling. We are in a space of unknown unknowns. Somehow we have to develop models that will be robust, that will perform predictably, even when we deploy them in the wild, and we can't characterize that wild, and they might face unknown unknowns. Next slide, please. In order to build robust models that are suitable for use when there are unknown unknowns or significant changes between the training environment and the test environment or in the wild, we have to go farther than just finding ways to quantify how well our model fits the data. We have to understand, measure the algorithm models system behavior or system response. We also have to find ways to characterize the model's stability, sensitivities to changes either in the data set or in the environment, or how to predict how it's going to perform if our assumptions don't hold. Next slide. Our work so far in developing methods to build robust AI models despite little data, and when we know that in the wild is going to be different, our successes so far is in developing super custom capabilities. Capabilities that really only work for that data set and that model and that specific application. And where we have been successful, we've drawn on a number of different approaches. Some of these approaches are super expertise driven. Sometimes they're experiments driven, while where we are trying to isolate some change in the model and link it to some change in the system. We also have techniques where we are intentionally training algorithms to be robust to anticipated noise conditions, sometimes by exposing the algorithm during training to intentionally noisified data sets, or doing something very clever with the architecture, like leveraging some adversarial approach that penalizes the network for paying attention to features that we think might be hidden in background in the real world. Next slide, please. In terms of research gaps, we need scalable, reusable techniques that are suitable for multiple applications. I'm also very interested in techniques to characterize the difference between the training environment and the target environment, or the training data set and the target data set, with the ultimate goal of predicting when the model will work well and when it will fail, particularly when we're transferring it to another setting, when we're deploying it in the wild. Next slide, please. Once we've detected an activity of interest, we try to characterize that activity in order to make predictions about an actor's capabilities, their intent, or their progress towards detecting or developing, their progress towards developing nuclear weapons. In the proliferation detection domain, these signals, if we can find them, they're faint. They're hard to detect among a complex and noisy background, and they're likely very sparse. Not just infrequent, but sparse, where we might detect one element of the pattern in one data set and another element in a completely different data set, or in a geographically different location or an entirely different time. Super sparse data. But we have one really interesting opportunity in the proliferation detection domain. The development of nuclear technologies requires a specific set of industrial activities, and certain of these activities are highly specialized, predictable, or well characterized. By well characterized, I mean we might have a lot of information, past data about them, or even physics-based or chemistry models describing that element of the system. Next slide, please. Domain-aware methods use computational techniques to combine what we know from the domain in whatever form that information is with data-driven models. In the proliferation detection domain, we're particularly interested in leveraging the well-characterized physics and industrial constraints of the process to develop nuclear weapons. And we refer to this process as the nuclear weapons fuel cycle. This slide here depicts the nuclear weapons fuel cycle, which starts with the extraction of uranium from the ground, that's called mining and milling, goes through chemical processing, enrichment, fabricating that into a nuclear weapon, and then test, which we talked about at the beginning of the presentation. How do we leverage everything that we know about this process, whether that comes from developing nuclear weapons ourselves or studying nuclear science and technology, to build more powerful artificial intelligence capabilities? Next slide. Example techniques in domain-aware methods that we've developed so far in my program are, again, super custom and draw on capabilities from a number of other fields in computing and analytics, like knowledge representation and system modeling. In terms of techniques to fuse heterogeneous data sources, our research has found it most promising to combine different data sources within some other underlying model structure, like a Bayes net or an activity-based model, like a discrete event simulation. We've been far more successful with this approach than the approach that we began with, which was dumping all of the different data sources into the same data frame and trying to find some super feature that somehow describes all of it. Next slide, please. Oh, I'll say on the preceding slide, I'm also very interested in expanding our concept of domain beyond that nuclear fuel cycle. So I talked about how the nuclear fuel cycle begins with the extraction of uranium out of the ground and ends with nuclear test. There are a number of other activities that a nation or program might pursue to develop nuclear weapons that either happen before mining and milling or are completely tangential to that. Activities such like pursuing research, acquiring specialized technology, attending a conference, we may be able to find indicators of those and also leverage domain information associated with those additional activities to build more powerful models. I hope that we can draw on other disciplines besides physics and chemistry, disciplines like economics and social science, to create more powerful AI systems. Next slide, please. When we are successful at developing a technology that supports proliferation detection, that technology will be used to support decision-making. It may be used to make decisions around diplomatic, military, or economic intervention, or to support national policy or strategic planning around the United States' nuclear stockpile or military capabilities. In the proliferation detection domain, decisions are high consequence. There's no room for error and little tolerance for false positives. Whether the technology that we produce is embedded within a larger technology system or deployed as a standalone software application and used by a human analyst, there is an end user to these technologies. These technologies have to be useful to somebody who, again, is making a decision using these technologies. And many times these end users require that the results and analyses produced by an AI algorithm must be transparent. Certainly many of us are familiar with explainability techniques, and these techniques are insightful. But how can we use them as a method or capability themselves, either to build trust in new artificial intelligence technologies or communicate some element of uncertainty to our end users? Next slide, please. When we talk about explainability or interpretability in artificial intelligence, sometimes we use those two words together. They do often come together, but represent two different concepts. Interpretability refers to, it's an intrinsic characteristic of a model. It refers to the level at which a model makes sense for a human observer, how much it matches your mental model for the system. Explainability techniques are an active capability that tries to clarify the internal functions of an AI system. Most explainability techniques use visualization-based approaches, and many of us have seen something like this image here with the husky, which really is a dog in the snow, as revealed by this explainability mask. Next slide. While breeding trust, building trust is really the most recognized use for explainability and interpretable methods. In my program, we have found success using these techniques to support both end use as well as model development. Researchers in my program use explainability tools as part of the model selection process to support the development of robust and domain-aware models. In the technique depicted on this slide, this research team developed a method where they use explainability techniques, the visualization, heat map-based approach, iteratively, while they're making changes either to the data or to the model or to what system state that whole setup is representing. Because of their understanding of the underlying physics, they're able to learn something about how the model is performing in response to what's happening in the system. And they're able to select a model that they predict will work best in the wild through this technique. Next slide, please. In terms of future research, explanation is really the first step when it comes to explainability and interpretable systems. I believe that if we can make these techniques, if we can take them from a visualization-based approach and turn them into computational methods, this will open doors for the development of responsible and transparent autonomous systems and optimized approaches to human-machine teaming. Next slide, please. Advances in data science and artificial intelligence present new opportunities for the proliferation detection community to exploit data at a scale that has been previously out of reach for us. This applies to existing traditional data streams like sensors. Perhaps now we can get through a ton more data or more high frequency data of the sensor of interest. And also entirely new data sources, ubiquitous data, Internet of Things, and in particular, unstructured data that we've not been able to leverage in the past. As I've said, the proliferation detection domain is highly technical and highly specialized. Our applications require specialized artificial intelligence systems, or at least I can say, while while it is beneficial to use generic tools like an image classification capability trained on generic ImageNet, we expect that we can achieve increased performance or develop more powerful AI techniques if we can specialize them for the unique aspects of our domain. Similarly, conventional data science techniques often don't work in our applications. Again, in proliferation detection, events are very rare, and the assumptions of independent and identically distributed random variables doesn't hold. That assumption is a fundamental assumption for many data science techniques. And so we have to find our own ways to leverage what data science makes possible by modifying some of these approaches so that they're suitable for the statistical characteristics of data in our domain. Next slide, please. In terms of future work, fine-tuning models is just the beginning. Fine-tuning models is important, and we know that it will be a key aspect to using artificial intelligence in proliferation detection. But how can we develop techniques to predict the degree of specialization, to predict the performance envelope when a specialization might fail? And how can we develop optimized pipelines to build specialized algorithms? Next slide. Finally, there are many barriers to the development and use of artificial intelligence for nuclear proliferation detection. There are scientific barriers, and we've discussed our approach to overcome and address many of these scientific barriers. But there are also non-scientific barriers to adoption, like lacking computer infrastructure, the need to modernize and update and make more sophisticated our data management practices, and a lack of available and relevant data for analysis. And saying lack of available data is even kind of an overstatement of it. We really have so little available data, particularly at the scales that are suitable or necessary for machine learning and artificial intelligence and other computational science analysis techniques. In the portfolio, in my program, we are investing in developing and sharing data sets in modalities that are relevant for proliferation detection, like modalities that look like what we'll get off of our sensors: spectral data, time series data, spectrograms, waveform data, in order to lower barriers to AI R&D and promote adoption across our community. Again, I'll say, and many of us recognize that artificial intelligence seems to be dominated by data modalities like images and text. Many of these modalities are not suitable for our applications. We need to build our own data sets, again, in relevant modalities for our domain, and develop techniques to analyze them. Next slide. In addition, we're developing and sharing practices like metadata. And I know metadata seems like standard operating procedure for many of us in data science and computing fields, but something like metadata, something as sophisticated when it comes to data management as metadata, is beyond standard practice for many in the nuclear security enterprise. Through efforts like this, we're transforming the entire proliferation detection community to make it more ready for AI technology and AI research and development. Next slide, please. So that's what we're up to in Next Gen AI and NNSA. And our progress in this field is only possible due to the efforts of researchers who are part of this program at national laboratories and universities across the United States. The data science portfolio, our next generation AI program, includes 30 projects. These projects range in duration, but typically they're about 2 years and include a project team of about 5 project team members. Though I do have 2 very large projects that include about 150 researchers from a myriad of backgrounds. As I mentioned, most of the projects are funded at the Department of Energy National Laboratories, but we also sponsor research by faculty and students at numerous US universities. Next slide, please. Each project team in my portfolio is pursuing an AI research project that, if they're successful, will solve an outstanding problem for US proliferation detection. This ensures that our efforts pursue the right new science, the right new mathematics that will not only advance the field, but also result in tangible improvements to national security. This also means that in addition to contributing to the academic literature through journal publications and conference presentations, project teams in my program also produce and deliver tangible products to our mission partners within the Department of Defense, intelligence community, and across the Department of Energy. Every year, these project teams transition about 50 new technologies to support operational proliferation detection missions across the United States government. These transitions take many forms. They include, as you would expect, models, code, and software applications. Also, as we discussed, data management approaches, architectures, and practices. These project teams produce technical reports and even, and I know you will appreciate, produce and share research-grade code and mission-relevant data sets. Now, in the few minutes I think I have left, I'd also like to share with you a few of the principles that I also share with project teams in my program to motivate and guide our efforts. I refer to these as myths and misconceptions for AI R&D in our program. Next slide. So first, an uninterpretable or unexplainable model is acceptable. And certainly by now you can appreciate why I have this here. Our technologies, the technologies that we develop, the AI systems we build, are used by end users and have to be useful for them. That demands that the tool be interpretable or explainable oftentimes to them. But the reason I have this as my #1 myth is that I communicate to my research teams that we have to prioritize the importance of the explainability of a model as much as we importance whatever classification or decision task that we're producing with the model as well. The requirement that the model is explainable is just as important as the AI task that the model is performing. And just as the certain mathematical method or techniques that you're using is informed by the sort of classification tasks that you're performing, the fact that the model has to be explainable and the nature that that explanation might take will also inform the model that you choose and the mathematics that you pursue in our research. So it's exceptionally important to recognize and to design for explainability from the get-go. Next slide. Myth 2, improving model performance is the only goal. And of course, I began this presentation with discussing the requirement for building robust AI systems. We're not looking only to improve precision and recall and accuracy, but also to improve our ability to improve the performance of models when we transition them to the wild. Next slide. My model or technique is good, it just needs more data. I hear this a lot, and I've even said this in the past as a researcher. We pick a technique, we like a technique, and then you come to the proliferation detection domain, and there just isn't enough data for that technique. Would you swear the technique would work if you just had more data? When we feel this in my program, we take it as an opportunity to pick a different technique or a different modeling approach or a different method that is a better fit for the domain. There is no more data in our domain. Now, there is a lot of information. It's not machine readable, and it's not in the same modality. It's not the same data type as a model that you're building, but we do have a lot of information. Using domain-aware methods, we'll try to extract and use that information in building next-gen AI. But sometimes we just need to pick a different technique that is a better match for the reality of data in the proliferation detection domain. Next slide, please. So I'm most excited about these last 2 myths. First, making models work per mission requirements is not R&D or is someone else's problem. Now, I remember when I was doing a lot of model development, there's this fun time in model building. If you can't tell, my background is mostly in model building. But there's this fun time, particularly if you're building like a framework where your model can do anything, it seems. And if someone with an application comes to you and asks, does your model work in this application? Will it work well? Your response is typically, it depends. In our next-gen AI research program, our research begins at it depends. It's very important research to go from, well, it depends, it could work, to figuring out the right way to make a specific model work to answer a specific question and to make it work really well. That is the sort of research that we tackle in this program. Next slide. And finally, our research cannot immediately or meaningfully affect national security assessments or decisions. Our research cannot meaningfully or immediately affect national security and make the world safer. And that absolutely is a myth. Every day, every minute, every second, right now, there are national security decision makers and national security analysts who look like you and look like me, whose job it is to make assessments and make decisions about pressing issues in nuclear proliferation. And their job is really hard, and they would love some additional capability or some help. Our research is aligned to solve these problems, and when we make progress, that means that in handing that tool over to an end user, to a national security analyst or decision maker, it will make their job easier. And in doing so, the techniques that we build, the technologies that we deliver to our end users and our mission partners do immediately and tangibly affect national security. Next slide. So I ask, and maybe you can put this up in the chat, which of these 5 myths did you find most surprising? Sometimes I get feedback from our research teams that myth number 3 hits hard, or they're excited to hear that there is a place for this sort of applied research where we take models from it depends to yes, I can answer this question. And I'll say for number 4, because I do feel very passionately about number 4, sometimes that means we have to hard code, we have to approximate, we have to move forward. But again, our whole goal in next-gen artificial intelligence for proliferation detection is to build useful models that enhance our ability to detect proliferation and make the world a safer place. Next slide. So I've talked a lot about the Department of Energy National Laboratories, and you might be wondering where they are. They're located across the country. I right now am in Washington, D.C., and as Aaron mentioned, I used to work at Pacific Northwest National Laboratory in the other Washington State on the west of the country. And everywhere in between are national laboratories. And I work with talented researchers from almost each of these national laboratories every day. Next slide. Actually, we'll go back that slide. We'll leave that up as we kind of wrap things up. As I said at the beginning of this presentation, the research that we're tackling in next-gen AI is incredibly challenging. All of the easy science is already solved. In fact, we know that we are on the right track when the research gets hard, when there are no longer any book answers, because that's the new math. And because we're working on real-world problems, we know that it is the right new math. Challenging the myths and misconceptions that I identified earlier keeps us on track towards advancing the science to develop useful AI technologies to improve US efforts to make the world safer from nuclear weapons threats. The use of nuclear weapons remains the most pressing challenge in national and international security. AI research and development at NSA is advancing the mathematics and science of artificial intelligence by developing new methods and techniques, particularly techniques that move beyond conventional machine learning to build the next generation of artificial intelligence. While our goal is proliferation detection, we believe that the potential for impact extends far beyond nuclear non-proliferation. The challenges posed by the nuclear security domain are so demanding that in building AI to detect early proliferation, we believe that we will advance the entire field of artificial intelligence. I'll leave with just this last slide that has my contact information. And I think at this point, Aaron, we can turn it over to you for any questions.
Yeah, we've got some great questions here. Before we get into those, I was wondering, Angie, if you would just take a minute or two and talk about, what is your job? What's a day in the life like for you? And how did you get to where you are?
Yeah, oh man, I'd be happy to. So I guess it kind of, maybe I'll start with what feels like the start of the process for me in terms of my daily job. So every year, my office, well, all the time, I'm working with partners across the US government to understand what the current gaps are in our capability to detect proliferation around the globe, to understand what the gaps are. And then I use my technical background to interpret those gaps and understand which ones I think we can solve with artificial intelligence. That helps to define where I think we're going as a research program. Every year, we open what's called a call for proposals. Many of us are familiar with the grant writing process to the national laboratories and also in another way to university partners to ask for ideas, ideas for new research projects that are responsive to these gaps and also in the area of next generation AI. And then I choose projects that I think are most likely to be successful. And if they are successful, will have the most impact for improving US proliferation detection capability. Then throughout the course of the year and the execution of each of those projects, I work with the project team. Very frequently, there are gaps, again, between our mission partner community and what research project teams know. So I help to align them to get them close together. I provide advice and also manage the day-to-day operations of the research project. How are they making progress against their scope? Do they have enough funding? Things like that. So that's sort of the day-to-day. I don't know if I do some other things. I inform policy. The United States government has lots of questions about artificial intelligence or nuclear nonproliferation. Sometimes I answer those. So that's a little bit of the day in the life. My route there is unexpected for me, but it makes sense looking back on it. When I began my career in the Air Force, I mean, that was before there was data science, but I was doing something similar to data science, operational analysis, operational analytics, ops research, trying to provide information to decision makers using whatever modeling or data analytics capability you could. As things go, my career in the military was really diverse. As Erin mentioned, I worked in intelligence, which gave me exposure to the intelligence community. There's also a truism in national security, particularly national security S&T, which is that it is a really small community. And no matter where you are in national security S&T, the goals are largely the same. The United States uses measurement technologies to detect bad guys, whatever the nature of those bad guys are. There are some giant threats that we're trying to prevent. So even though I wasn't working in the National Laboratory Complex, I was working very close throughout my whole career in the Air Force. When I started at the Air Force Research Lab, when I moved to the Intelligence Center, it all ended up being the same community that I found when I finally transitioned to the National Laboratory Complex. When I got to the national labs, I began to do the business of research. I was a researcher myself, got my hands dirty writing code, that sort of thing, but moved, particularly leveraging my background and my understanding of the operational setting, understanding of warfighting and how end users would use the technology, moved into project management and also the development of research concepts and helping to align what was happening at PNNL to what outstanding mission challenges there were across the national security enterprise. And then, and I hope this happens to all of you, but I got this opportunity to come to Washington, D.C. to do something kind of outside my comfort zone and to sit at headquarters like I am now, but to advise the entire portfolio. So before becoming the program manager at NNSA, I was what we call a technical advisor. So a researcher still employed by the National Laboratory, but with the responsibility of analyzing the technical rigor of each project in the program. And I'll say, if you ever have an opportunity to do something like that and you're interested, I would encourage you to take it, because even just the opportunity to see 30 projects happen at hundreds of research organizations at one time, I mean, you just become such a more informed, capable, and creative researcher, even in that experience. I loved it. I loved that job and was kind of good at it. So the government asked me to join as a Fed. And so I transitioned into the program manager role and I'm in that role now. Did that hit the wickets, Erin?
Yeah, absolutely. So I'm going to kind of amalgamate a bunch of the questions here, but there's a lot of interest in getting your assessment on like what is the right mathematical background or what are the right mathematics skills that you think are best for researchers coming into this area?
Yeah, creativity and bravery, cleverness, and honestly, a real willingness to, this is going to sound trite, I'd say a willingness to dig in. Again, like what was it before that talks about research beginning at it depends. There's a real reticence to doing the work that starts at it depends, because we want to stay in this really abstract land where, again, the model could do everything. When you move to more specific than it depends, not only are you moving away from having a model that could do anything, you're also, I'm notorious for using bad sports analogies, but it's kind of like pool. When you call your pocket, you're saying, I'm going to try to do that. And it's super high risk that you're going to fail. After all, there's that trite phrase, all models are wrong. So you're saying, I'm going to try to do that exact thing. And it's really risky that you're not going to be successful. So whatever it takes to be willing to do that, like I said, bravery, cleverness, creativity, that's what I think makes people most successful. But really, it's no one thing. And I think, as I said, because this work is so hard and we're completely off book, there's no particular background that makes you any better suited for being successful in this area than any other. But I will say, as I was saying that, I did think, and I'm not just saying this because this is joint mathematics meeting, but I do think that the background that you get in mathematics and statistics not only is particularly well suited for this domain because we're doing so much modeling, because you're really operating with, I mean, if you were a physicist, you would talk about the conservation of energy. For us, we're talking about the conservation of information. And I think we can do that, those of us with mathematics backgrounds and an understanding of modeling. I do think that the background in mathematics and statistics makes for a fantastic mindset for this domain. I'll also say that though I did highlight all of those mathematicians in the program, we aren't the bulk of folks in proliferation detection. Really, most people in proliferation detection have backgrounds in physics, chemistry, the life sciences, engineering, and they bring really important capability to the problem. But mathematicians and statisticians bring a whole different mindset. And it's super important that we have both of those mindsets to solve these problems. And I would even say, I wish that we had more mathematicians and statisticians who would bring their way of breaking down the problems to solve proliferation detection challenges.
Okay, so a slightly easier one. Somebody asked if you could talk just a little bit more about the Russian bunker that was at the beginning of your slides.
Oh, yeah. First, I was like, wait, what's that question going to be? Yeah, absolutely. So I can't remember. I don't remember what slide that is. I don't know if our tech support can flip back to it. But one of the oldest capabilities for proliferation detection that comes from that, first initial detecting nuclear detonations is looking for signatures of nuclear explosions in seismic waves. So think of like the Richter scale, like how you look for earthquakes. So that is, and there's all sorts of geophysics, the physics of waves through Earth that make this super interesting. But suffice it to say, we rely on seismic monitoring stations stationed around the world to monitor, activity in the Earth to try to find explosions. And there's a really interesting problem. We have some work in AI, using AI, machine learning, and other things to disambiguate between an earthquake and an explosion. So that station in Russia, maybe flip one, another, maybe a couple more, 2 or 3 more. Anyway, that station in Russia is a seismic monitoring station. There we go. Oh, one previous. They are located all around the globe. There are also hydroacoustic monitoring stations that detect the propagation of waveforms through water. So that one is deployed, I should have mentioned, by the CTBTO, the Commission Banning Nuclear Tests and Treaties. They are an international organization similar to the IAEA with the role of maintaining those stations. Those are one of the global partners that the United States works with in nuclear proliferation detection.
Can you speak for a minute about the extent to which political leaders use the input gleaned by the work developed out of your offices for, basically how much are they actually using the tools, and how is the work being done in your portfolio actually informing decisions?
Yeah, I mean, as a portfolio, AI is very new. So let's say we've been doing this work really very well for only a couple years. And we have transitioned, I think, a handful of models and technologies to the point that they might be used in this way. Often what happens is there is a national security analyst who is watching a particular activity of interest, looking for these pieces of evidence, looking for this information. And the techniques, the technologies that we produce are just one of the data sources that they rely on, or analysis methodologies that they rely on. They're kind of like a detective. If you think of those detectives with the pushpin boards, and all of the pictures of faces and things like that, looking for connections, think of something coming out of our tool as one of those elements on their detective board. And increasingly, I would say increasingly, what we think of in terms of transitioning these capabilities to the national security enterprise is that more and more of those little elements on the analysts or detectives pinboard will come from technologies that we produce. So I don't know, that speaks to it directly. I would say we've transitioned a handful and they're used in this way. That's probably the most straightforward way I can answer that.
Okay, so another hopefully easy one. What is there a difference between the red and the blue labs in that map?
Oh, probably yes, there absolutely are. So Department of Energy laboratories each have different missions. Some of the laboratories have missions commissioned by the Office of Science, where they're pursuing fundamental and basic research towards the fundamental sciences. Others are energy labs, where they might be pursuing the development of energy technologies, renewable energies. Their efforts might be directed towards the energy grids. Other of these laboratories are chartered to support the National Nuclear Security Administration. Predominantly, they do nuclear weapons development and sustainment. So that color coding has to do with which part of Department of Energy has commissioned that laboratory and what their overall mission is, whether it's science, energy, or national security.
Okay, do you have interest in models that are trying to go after human behavior, like game theory type things?
Yes, absolutely.
Like for what?
Like for what? I mean, all sorts of different approaches. I mean, I think we certainly the structure of game theory can be used, within something like an adversarial neural net. So we're interested in that. I also think there are opportunities to use structures like game theory or other optimization approaches from system modeling to build domain-aware methods. But I think the question is really getting at, are we looking to understand human behavior and maybe use game theory to do some of that? And I would also say yes, particularly when I talked about extending our concept of the nuclear fuel cycle and the sorts of activities that might be indicative of nuclear proliferation. I think some of that stuff related to what humans are doing is now tractable with the pursuit of signatures related to what humans are doing is now more tractable with AI, with techniques like game theory and unstructured data sources. So for a couple different reasons, I say yes to techniques like game theory.
And are there resources available to the public to learn about or apply the approaches and techniques that your research teams have developed?
Yeah, absolutely. We publish a lot in the open literature, so you can find it if you were to Google. We also document all of our publications in what is called the Department of Energy's Office of Science and Technology Information, OSTI. So that's a good resource if you're going strictly for what we published. But yeah, it's out there. Increasingly, we are open sourcing our code. I don't know if my slides are available, but I put some links in there. We're open sourcing our code, so you could Google them and you might turn them up. But yes, yeah, like I said, we are members of the academic community and publish in academic literature and encourage people to use that work.
Okay, thank you very much. If you have any other comments, like for students and how, like what's the best way for them to try to get involved in our enterprise, that would be great.
Yeah, absolutely. So I don't think I mentioned it, I failed to mention it, but there are a number of different opportunities for students to participate in the Department of Energy National Laboratory Complex. Probably all of the laboratories offer internships. Some of them in structured internship programs, like internship programs to develop another element of nuclear nonproliferation is called safeguards. There are safeguards-oriented programs. Livermore National Laboratory runs a data science institute for the development and application of data science techniques for national security applications. Each lab sort of has different internships. That's a good references list. Many of those are programmed for whoever asked about the availability of our work in the literature. But anyway, lots of internship programs either run out of the laboratories. NNSA runs an internship program or a research fellowship type program on our own where we sponsor research. So I bet you're asking for where is a good place to start. The best place to start would be to go to the website of the laboratory that you're interested in, whether that's a near or far laboratory from you, and looking for their available internship programs. That's a fantastic place to start. And many of our researchers, many of those faces on the slides that we saw before, their pipeline to the National Laboratory Complex began with internship programs, research associateships following a master's degree or a postdoc type program at the National Laboratories. I could speak in more detail about this, but certainly that is a pipeline to participate in an internship program or have your research funded by the National Laboratories and then join the complex. And again, going to the National Labs websites is a great place to start.
Excellent. Thank you very much. We have one last minute here to pipe in some last questions. And I'll just sort of stomp what Angie just said about internships at the laboratories. I've seen on the attendance list here, there's actually quite a few of us from the National Laboratories, and we would love for any of you guys to reach out to all of us, and just like Googling internship at National Labs will get you a lot of stuff. So I think that that's all we've got here for today. Thank you everybody for showing up. And thank you very much to Angie for giving this wonderful presentation. We all greatly appreciate it. We sort of give the Zoom clap. I don't know what the correct way of doing that is, but thank you very much.
I think you did it right, Aaron.
And thanks everyone for coming. Have a great day.
Thank you, Aaron. Thanks, everyone.